Welcome! In this session, we will explore a fascinating SQL problem titled The Number of Employees Which Report to Each Employee. Together, we'll break down the problem, analyze the hierarchical structure of the data, and solve it step by step. Let's dive in. The problem we are solving involves a table called employees, which contains data about employees in a company. This table has three columns: employee_ID, name, and manager_ID. The employee_ID is the unique identifier for each employee and serves as the primary key of the table. The name column contains the name of the employee, and the manager_ID column specifies the ID of the employee's manager. If an employee doesn't have a manager, the manager_ID will be set to null. This structure allows us to represent a hierarchical relationship between employees and their managers. Our task is to write an SQL query that generates a report showing the number of employees who report directly to each manager. The report must include two columns: manager_ID, which is the ID of the manager, and report_count, which represents the total number of employees that directly report to that manager. If a manager does not have any direct reports, their manager_ID must still be included in the output, with a report_count of 0. Additionally, the results should be sorted in ascending order based on the manager_ID. The input for this problem is the employees table, which contains the three columns: employee_ID, name, and manager_ID. The employee_ID is an integer that uniquely identifies an employee. The name is a string representing the employee's name, and the manager_ID is an integer that points to the employee_ID of the corresponding manager or is null if the employee has no manager. The output of our query should be a table with two columns: manager_ID and report_count. The manager_ID column will list the IDs of the managers, and the report_count column will show how many employees directly report to each manager. Let's look at an example to better understand the problem. Consider an employees table with 5 rows. Alice, with employee_ID equals 1, does not have a manager, as indicated by a null value in the manager_ID column. Bob and Charlie report directly to Alice, while David and Eve report directly to Bob. The output for this data will show that Alice, as a manager, has a report_count of 2 because Bob and Charlie report to her. Similarly, Bob has a report_count of 2 because David and Eve report to him. Charlie, David, and Eve do not manage anyone, so their report_count is 0. Breaking down the explanation further, Alice, whose employee_ID is 1, has Bob and Charlie in her team, so the report_count for manager_ID equals 1 is 2. Bob, with employee_ID equals 2, manages David and Eve, resulting in a report_count of 2 for manager_ID equals 2. On the other hand, Charlie, David, and Eve, with employee_ID values of 3, 4, and 5 respectively, do not manage anyone, so their report_count values are all 0. This approach ensures that every manager is included in the output, even if they have no direct reports. Now, consider a second example where the employees table contains 3 rows. Alice, with employee_ID equals 1, is a manager and has Bob directly reporting to her. Charlie, with employee_ID equals 3, does not have a manager, as indicated by a null value in the manager_ID column. The output shows that Alice has a report_count of 1 because only Bob reports to her. Bob and Charlie, with employee_ID values of 2 and 3 respectively, do not manage anyone, so their report_count values are 0. This ensures that all employees are accounted for, regardless of whether they manage others. Finally, there are some constraints to be aware of. The employees table will have at most 10,000 rows, and the employee_ID column is guaranteed to have unique values. The manager_ID column can contain null values for employees without a manager. The output must be sorted in ascending order of manager_ID, and there will not be any cyclic relationships in the data. This means no employee will ever manage themselves, either directly or indirectly. These constraints ensure the problem remains well-defined and computationally feasible. To tackle the problem of counting the number of employees who report to each manager, we can take advantage of the hierarchical structure in the employees table. This table typically includes columns such as employee_ID, representing the unique ID of each employee, and manager_ID, which identifies the employee's direct manager. One possible approach to this problem is the brute force method using nested queries. Here, for every unique manager_ID, we count the number of employee_ID entries that have the same manager. While this method is conceptually simple, it requires a subquery for each distinct manager, leading to a time complexity of about O(m*n), where m is the number of managers and n is the number of rows. This makes it inefficient, especially for large datasets, as it involves redundant calculations. On the other hand, we can consider an optimized approach using the group by clause in SQL. By grouping all employees based on their manager_ID, we can count the number of employees in each group, avoiding the repetitive computation seen in the brute force method. This idea forms the basis of a much more efficient solution. The implementation of this optimized approach is straightforward. We use a single SQL query that groups rows by manager_ID and applies the count function to determine the number of employees in each group. The query looks like this: select manager_ID, count, employee_ID, as_report_count from employees group by manager_ID. This query processes each row in the table exactly once, resulting in a time complexity of O(n), where n is the total number of rows. Compared to the brute force method, it eliminates the need for nested subqueries and redundant computations, making it significantly faster and more scalable. However, this approach does assume that the database engine optimizes the group by operation, which is generally true for modern database systems. Given its efficiency and simplicity, this approach is well suited for this problem and aligns with SQL best practices for aggregation tasks. The decision to use the group by approach was based on its efficiency, simplicity, and scalability. By consolidating rows based on manager_ID, we reduce computational overhead and achieve a time complexity of O(n). This makes it highly efficient for large datasets. The solution is also compact and leverages standard SQL functions, making it easier to implement and maintain. In comparison, the brute force approach is more intuitive but suffers from poor scalability, which makes it impractical for real-world applications. While other methods, such as recursive queries, could handle more complex hierarchical relationships, they are unnecessary for this problem since we are only concerned with direct reports. Overall, the group by method strikes the right balance between performance and simplicity, making it the optimal choice for solving this problem effectively in a wide range of scenarios. To solve this problem, we need to determine how many employees report to each employee in an organization, including both direct and indirect reports. The organizational hierarchy is defined in the employees table, where each row represents an employee. The employee_ID uniquely identifies each employee, and the manager_ID points to their direct manager. If manager_ID is null, the employee is at the top of the hierarchy, such as the CEO. This hierarchical structure forms a tree, where each employee is either a node with subordinates or a leaf with no direct reports. The challenge is to calculate the total number of employees reporting to each individual, which requires traversing this tree structure. This traversal must include both immediate subordinates and the employees reporting to those subordinates, making the problem inherently recursive. By leveraging this recursive relationship, we can accurately compute the report counts for every employee. The recursive relationship at the core of this problem can be expressed as the total report count for an employee being equal to their direct reports plus the cumulative counts of all their subordinates. In mathematical terms, the total count for an employee is the sum of the direct reports and the total counts of the employees reporting to them. SQL provides a powerful feature called recursive common table expressions, or CTEs, which is well suited for this hierarchical computation. The solution involves three main steps. First, we establish the direct relationships by selecting employee_ID and manager_ID from the table. Next, we define a recursive CTE that starts with these direct relationships and propagates the report counts upward through the hierarchy by iteratively adding the counts of subordinates. Finally, we aggregate the results using a group by clause to calculate the total reports for each employee. The SQL implementation begins with a recursive CTE named employee hierarchy. The base case of the recursion identifies the direct relationships between employees and their managers, selecting each employee and their manager with an initial depth of 0. The recursive step extends this hierarchy by joining the employees table with the CTE on the condition that the employee underscore ID matches the manager underscore ID. This step accumulates indirect relationships by traversing the hierarchy and incrementing the depth at each recursive level. Once the hierarchy is fully built, we aggregate the results. The final query selects each manager and counts the distinct subordinates reporting to them, both directly and indirectly, grouping the results by the manager underscore ID. This approach effectively computes the total reports for every employee in the organization. The output of this query is a table where each row corresponds to a manager and the total number of employees reporting to them. The manager underscore ID column identifies the manager, and the total underscore reports column provides the calculated count of their direct and indirect subordinates. This query utilizes recursion to capture the hierarchical relationships, allowing it to handle complex reporting structures efficiently. Several insights emerge from this problem. First, the recursive nature of the computation is essential for capturing both direct and indirect reporting relationships, which are core to the problem. Second, recursive CTEs in SQL are highly optimized for traversing hierarchical data, making them the ideal choice for this task. Lastly, edge cases like organizations with a single employee or data with disconnected subhierarchies can be handled gracefully. However, cycles in the hierarchy, which are not typically expected, could lead to infinite recursion. To prevent this, safeguards such as a maximum recursion depth or cycle detection can be implemented. The employees table serves as a directed acyclic graph, or DAG, where each edge points from an employee to their manager. This structure is traversed using the recursive CTE, which acts like a temporary table to propagate the counts of reports through the hierarchy. Internally, the SQL engine relies on indexing and hashing to perform joins and group operations efficiently, which can be likened to using a hash map for fast lookups. Optimizations such as adding an index on the manager underscore ID column can significantly improve the performance of recursive joins. Additionally, depth limiting can be employed to safeguard against data anomalies like cyclic relationships, which could result in runaway recursion. For organizations where the hierarchy is relatively static, pre-computing and storing the report counts in a separate table can further enhance performance by enabling faster querying. The computational complexity of this solution is determined by the size and shape of the hierarchy. Traversing the hierarchy involves visiting each employee once, resulting in a time complexity of O(n) for n employees. Each join operation within the recursive CTE benefits from indexing, reducing the complexity of individual joins to O log n. Consequently, the overall time complexity is approximately O(n * log n). The space complexity depends on the maximum depth of the hierarchy, as the recursive CTE uses temporary storage proportional to the depth. This makes the space complexity O(d), where d is the maximum depth of the hierarchy. By combining efficient traversal, indexing, and storage techniques, the algorithm achieves a balance between computational efficiency and scalability, making it suitable for large organizational datasets. Here, we start by importing the default dict class from the collections module. This will help us create a dictionary that initializes default values automatically, which is useful for counting employees. Next, we define a class solution and a method count employees. Inside this method, we initialize two dictionaries. The first, reports underscore count, will store the total number of employees reporting to each manager. The second, manager underscore map, maps each employee to their respective manager. We then parse the input list of employee manager pairs to fill manager underscore map. This mapping allows us to know who reports to whom. Afterward, we define a helper function called DFS, which is short for depth first search. This function will compute the total number of reports for a given employee recursively. The first step in this function is to check if the employee's report count has already been computed and stored in reports underscore count. If so, we simply return the cached value. Otherwise, we initialize the total reports to 0 and begin iterating over all employees in the manager underscore map to identify those who directly report to the current employee. For each of these direct reports, we add one for the employee and recursively include all their indirect reports as well. The recursive process continues by adding the counts from the DFS function for each direct report. Once the total number of reports for an employee is calculated, we store this value in the reports_count dictionary to avoid redundant computations later. The function then returns the calculated value for use in further computations. After defining the helper function, we proceed to compute the reports for all employees in the manager_map. This ensures that every employee's report count is calculated, even if they are not explicitly referenced in earlier recursive calls. Once this is complete, we prepare the result in the required format. We iterate over all employees in manager_map.keys and append a tuple for each employee, containing their ID and the total count of reports from reports_count. This ensures that the final output is formatted as a list of tuples, where each tuple represents an employee and their respective total report count. The method then returns this result, which provides the desired information in a clear and structured format. Finally, we see an example usage of the countEmployees method. The employees list represents the organizational hierarchy, where each tuple contains an employee ID and the ID of their manager. For instance, employee 1 is the CEO and has no manager, while employees 2 and 3 report directly to the CEO. Similarly, employees 4 and 5 report to employee 2. We create an instance of the solution class and call the countEmployees method with the employees list as input. The result is printed using the print function, which will display the total number of employees reporting to each employee, including both direct and indirect reports. This demonstrates how the solution works in practice and verifies that the logic accurately computes the desired output for the given hierarchy. Here, we start by defining a Java class called solution, which contains the method countEmployees. This method takes a two-dimensional array of employees as input. Each element in this array represents an employee-manager pair, where the first value is the employee's ID and the second value is their manager's ID. If the manager ID is -1, it means the employee does not have a manager, typically representing the CEO. We initialize two hash maps. The first one, reports count, will store the number of employees reporting to each manager. The second, manager map, maps each employee to their direct manager. Next, we iterate through the employees array to populate the manager map. For each employee-manager pair, we assign the employee ID as the key and their manager ID as the value, with the manager set to null if the ID is -1. Additionally, we define a memoization hash map to store results of previously calculated report counts, improving the efficiency of recursive calculations. Lastly, we declare a helper method, DFS, which will be used to recursively calculate the total number of reports for a given employee. In the DFS method, we first check if the result for the current employee ID is already in the memoization map. If it is, we return the stored value to avoid redundant calculations. Otherwise, we initialize a variable, total reports, to 0. We then iterate through the entries in manager map. For each entry, if the value matches the current employee ID, it means the corresponding key is a direct report. We increment the total reports by 1 and make a recursive call to DFS for the direct report, adding its report count to the total. After calculating the total reports for the current employee, we store the result in the memoization map and return the value. Once the DFS method is complete, we iterate through all employee IDs in the manager map and call DFS for each one to ensure every employee's report count is calculated. After that, we prepare the result as a list of integer arrays. Each array contains an employee ID and their corresponding report count, retrieved from the memo map. This result is then returned as the output of the countEmployees method. Finally, we include an example in the main method to demonstrate how the solution works in practice. We define a sample input, employees, which is a two-dimensional array representing the employee-manager relationships. For instance, employee 1 has no manager, while employees 2 and 3 report to employee 1, and so on. We then call the countEmployees method with this input and store the result. To display the output, we iterate through the result list and print each employee ID along with their respective report count. This provides a clear, visual representation of how many employees report to each person in the hierarchy. Here, we start with a small hierarchy where employee 1 is the CEO, and employees 2 and 3 both directly report to employee 1. To solve the problem, we first initialize two data structures, reports_count, which will keep track of how many employees report to each manager, and manager_map, which will map each employee to their respective manager. We then build the manager_map by iterating through the input. For each employee-manager pair, we add the entry to manager_map. For example, since employee 1 has no manager, we add 1, none. Similarly, for employees 2 and 3, who report to 1, we add 2, 1, and 3, 1. By the end of this step, our manager_map contains 1, none, 2, 1, 3, 1. Next, we use a depth-first search, or DFS, to calculate the number of employees reporting to each manager. Starting with the CEO, employee 1, we initialize the total reports for employee 1 to 0. We then look for employees who directly report to employee 1, which are employees 2 and 3, and recursively call the DFS function for each of them. For employee 2, since no one reports to them, their reports_count is set to 0. Similarly, for employee 3, their reports_count is also 0. Returning to employee 1, we calculate their total reports as the sum of the reports from their direct employees, which is 1 for employee 2 and 1 for employee 3, resulting in a total of 2. We store this value in reports_count as reports_count, 1 equals 2. Finally, we construct the result by converting reports_count into the required output format, which gives us 1, 2, 2, 0, 3, 0 for this example. Now, we analyze a larger hierarchy where employee 1 is still the CEO, but there are additional levels of reporting. Employees 2 and 3 still report to employee 1, but now employees 4 and 5 report to employee 2. We begin by initializing reports_count and manager_map as empty, and then populate manager_map from the input. After processing all employee-manager pairs, the manager_map becomes 1, none, 2, 1, 3, 1, 4, 2, 5, 2. Next, we calculate the reports using DFS. Starting with employee 1, we initialize their total reports to 0 and identify employees 2 and 3 as their direct reports. For employee 2, we again initialize their total reports to 0 and find employees 4 and 5 as their direct reports. For both employees 4 and 5, since they have no one reporting to them, their reports_count is set to 0. Returning to employee 2, we calculate their total reports as 1 for employee 4 plus 1 for employee 5, resulting in a total of 2, which we store as reports_count, 2 equals 2. For employee 3, we see that no one directly reports to them, so their reports_count is set to 0. Returning to employee 1, we calculate their total reports as the sum of reports from employees 2 and 3. For employee 2, this includes the 2 reports from employees 4 and 5, and for employee 3, it includes their 0 reports. Adding these together, employee 1 has a total of 3 direct and indirect reports, which we store as reports_count, 1 equals 4. Finally, we convert reports_count into the output format to get 1, 4, 2, 2, 3, 0, 4, 0, 5, 0, which captures the hierarchy and reporting structure for all employees. In the case of a single employee, such as employee 1, who is the CEO with no other employees in the hierarchy, the process is straightforward. We initialize reports_count and manager_map as empty, and then populate manager_map with the single entry 1, none, indicating that employee 1 has no manager. When we perform the DFS for employee 1, we find that they have no direct reports, so we set reports_count, 1 equals 0. Converting this into the result format gives us 1, 0, which clearly shows that there are no employees reporting to employee 1. This concludes the solution walkthrough for all examples. To analyze the time complexity of our solution, let's break it down into 3 main steps. First, we build the manager_map by iterating through the employee's input exactly once. Since we are processing each employee-manager pair in the input, this step requires n time, where n is the total number of pairs. Next, the recursive depth-first search, or DFS, is invoked for each employee exactly once. Within each DFS call, we process the corresponding manager's direct reports by iterating through the manager_map. Despite this inner loop, every employee is only processed once overall because the results are memoized in the reports_count dictionary. This ensures that the total work done by all the DFS calls combined is bounded by n. Finally, the result list is constructed by iterating through all n employees, which also takes n time. When we combine these steps, we get an overall time complexity of O(n) plus O(n) plus O(n), which simplifies to O(n). The space complexity of the solution is determined by three main factors. First, the manager_map dictionary stores one entry for each employee. Since there are n employees, this requires O(n) space. Similarly, the reports_count dictionary also stores one entry per employee, contributing another O(n) space. The recursive call stack for the DFS function depends on the depth of the management hierarchy tree. In the worst-case scenario, where the hierarchy forms a single chain of employees, the recursion depth could reach O(n). On the other hand, in the best-case scenario of a flat hierarchy, where the CEO directly manages all employees, the recursion depth is only O(1). Combining these factors, the overall space complexity in the worst case is O(n), as the dictionaries dominate the space usage. The best, average, and worst-case scenarios help us understand how the algorithm performs across different hierarchy structures. In the best case, with a flat hierarchy where all employees report directly to the CEO, the DFS function terminates quickly for each employee without making further recursive calls. While the recursion depth is O(1), in this case, the overall time complexity remains O(n), since all employees are processed. In a balanced hierarchy, the recursion depth becomes proportional to the logarithm of the number of employees, or O log n. However, the time complexity is still O(n), because each employee is processed exactly once. In the worst case, where the hierarchy forms a chain-like structure, the recursion depth reaches O(n). Even in this scenario, the time complexity remains O(n). By contrast, a naive approach that recalculates the report counts for every employee without memoization would involve iterating through the input list repeatedly, resulting in an O(n)² time complexity. Our use of memoization ensures that each employee is processed once, avoiding redundant calculations and achieving linear time complexity. The mathematical justification for the efficiency of this solution lies in the use of memoization. By storing each employee's report count in the reports_count dictionary after it is calculated, we eliminate redundant computations. This ensures that the DFS traversal only visits each employee once, leading directly to a linear time complexity of O(n). Additionally, the overall space complexity is dominated by the storage of the manager_map and reports_count dictionaries. Since each dictionary contains one entry per employee, their combined space usage is O(n). Therefore, both the time and space complexities of the solution are optimal at O(n), making it highly efficient for this problem. In working with hierarchical data, there are several common mistakes to watch out for. One of the biggest pitfalls is using an incorrect join condition. For example, mistakenly joining on employee_ID equals manager_ID instead of manager_ID equals employee_ID can completely misrepresent the hierarchy or even result in no output. It's essential to ensure the logic accurately reflects the relationship between employees and their managers. Another issue arises when failing to handle null values for top-level managers. These managers often have no manager_ID, so if your query doesn't account for that, it could lead to missing data or incorrect aggregations. Performance is another area of concern. Queries involving large datasets can become inefficient if non-indexed columns are used in joins or if nested subqueries are over-relied upon. To address this, ensure that employee_ID and manager_ID are indexed for faster execution. Additionally, duplicate data in the employees table can inflate results, so you should always validate data integrity beforehand. Finally, it's important to understand the structure of the hierarchy itself. Assuming a strict tree structure where each employee has one manager, or overlooking potential edge cases like cycles or missing links, can lead to errors. Always clarify these assumptions before proceeding. When approaching hierarchical problems in interviews, there are several key insights to keep in mind. First, take the time to visualize the hierarchy. Drawing out the organizational structure can help you better understand the parent-child relationships, which is critical for crafting an accurate query. Recursive Common Table Expressions, or CTEs, are often the go-to solution for these problems. They allow you to elegantly traverse hierarchical data, but you must clearly explain the base case and recursive logic to your interviewer. Keep in mind that some databases may not support recursive CTEs, so you should be prepared to write iterative queries as an alternative. It's also important to discuss edge cases. These might include scenarios like disconnected graphs, circular references within the hierarchy, or employees with missing managers. Even if you don't solve them during the interview, showing awareness of these challenges demonstrates your thorough understanding. Lastly, be ready to discuss performance optimization strategies. For large datasets, you can talk about indexing, limiting recursion depth, or even using materialized views to manage performance. And if you want to explore related problems, questions like LeetCode 1615, 197, 173, and 112 can help you build on similar concepts such as hierarchy visualization and tree traversal. There are also a few alternative approaches to consider when solving hierarchical problems. Recursive CTEs are a popular choice because they provide a concise and natural way to traverse hierarchies. However, they can struggle with performance issues if the hierarchy is especially deep. To mitigate this, it's important to define a clear recursion depth to prevent runaway queries. For databases that don't support recursive CTEs, iterative queries can be a useful alternative. While these solutions are less intuitive and harder to explain, they can still get the job done. Another option is using materialized views. By pre-computing the employee counts and updating them periodically, you can significantly improve query performance for static or rarely changing datasets. However, this comes at the cost of real-time accuracy. When deciding on the best approach, you'll need to weigh the trade-offs. Recursive CTEs offer simplicity and readability but may not be the best choice for extremely large or complex hierarchies. Iterative solutions, while more complex, can be optimized for better performance. Similarly, there's a balance between real-time results and pre-computed data. Real-time queries ensure the most up-to-date counts but may be slower, whereas pre-computed results provide faster query speeds but sacrifice immediate accuracy. Understanding these trade-offs is key to selecting the right solution for your specific use case. Great job! We've successfully tackled the SQL problem of counting employees reporting to their managers. Remember, mastering SQL is a valuable skill for both interviews and real-world scenarios. Don't forget to practice similar problems to reinforce what you've learned. Thank you for joining, and stay tuned for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!